Okay, let's start by talking about pressure and stress. All right? Here, let's switch over to the notebook. So a pressure is a force per unit area. Okay? And pressure has units of newtons per meter squared, of course. And 1 Newton per meter squared is 1 Pascal of pressure. But we want to be careful. What we mean by a force here is a force that's applied to the surface of our object, like so, okay? And so the force that we want is this force applied normal to the surface, and the area that we're interested in is, in this case, the area of the top of the cube. It's the area that the force is applied to, okay? This type of pressure is also called compressive stress. Okay? Just to illustrate this idea, which I think is probably familiar, we can do a quick example. We can figure out the pressure beneath a 1 meter by 1 meter by 1 meter cube of water. Okay? So let's suppose the cube we're talking about is this one, but it's made of water. And we're interested in the compressive stress that this cube exerts on the surface that it's sitting on. Of course, there's a force acting on the surface because the water is sitting in the Earth's gravity, and the force is just m times g, okay? The mass is the mass of 1 cubic meter of water, which is 1,000 kilograms. And g here is just 9.8 meters per second squared, the acceleration of gravity at the surface of the Earth. On the other hand, the area that the force is applied over is just the 1 meter squared area of the bottom of the cube. And so the pressure is clearly the product of these two, 9,800, divided by the area, which is 1. And so we have 9,800 newtons per meter squared, or 9,800 pascals. Oops. I just wanted to make a box around the answer. Or expressed another way, this is about a tenth of an atmosphere. Because 1 atmosphere is also, we're talking about the atmospheric pressure, is also described in pascals, and it's about 100,000 pascals. Actually, 1.013 times 10 to the 5th pascals. And the pressure due to the water is about 10 to the 4, or 1/10 of that. Okay? Now, a stress is a generalization of this idea. So a stress, sigma, is always a force over an area, but now the force doesn't have to be applied in the same way. Generally, there are 3 types of stress that we can think of. Here, let me try drawing this square once more. There we are. Ah, perfect. We could have a compressive stress, as we mentioned before, where the force applied is normal to the surfaces and it's inward, it's squishing the material, okay? We could have likewise, but similar, we could have other types of stress. There are two more that we'll be interested in. The second type is called tensile stress. And in tensile stress, the arrows point outward instead of inward. Okay? And finally, we could have shear stress. In shear stress, the force is not normal to the surface, but is parallel to it, like so. And shear stress maybe is the one that's least familiar and takes a little bit of thought. We can illustrate these different types of stress by considering some rather familiar examples. Imagine a mass that's supported from the ceiling because it's hanging from a string. Oh my goodness. There we go. There's our mass. Then the string is clearly under tensile stress. Okay? We talk of the tension in the string. That's just a measure of tensile stress. Now imagine something else. Suppose that instead of being attached to the ceiling, our block is glued to the wall. Then the weight of the object acting on the wall where it's attached is an example of shear stress. All right? In particular, the glue that's joining them together, let's say, if it's glued to the wall, the glue would be under shear stress. In real life, things can be more complicated. We can have more than one type of stress acting at the same time. For example, in this case, where our mass is attached to the wall, oops, then at the center of the glue joint, we would have shear stress. But clearly at the top of the glue joint, we would also have tensile stress because the object would want to kind of rotate as it came off, okay? So it's pulling it away. And likewise on the bottom, we might have compressive stress. So we can have combinations as well. Anyway, that's an illustration of the three types of stress that we're going to worry about: compressive, tensile, and shear. Okay? Here, let's do a quick example of shear stress. Here's the picture that we just drew. Our block attached to the wall with some mass, just shade it in so we can see it here. It's going to be attached to the wall with some glue. And we want to know if the glue will hold. Let's suppose the block has dimensions 10 centimeters by 10 centimeters by 5 centimeters. So this distance is 5 centimeters and this is 10. And let's suppose it's made of iron so that it has a density. So here, I'll write as 8 grams per centimeter squared, centimeter cubed. Okay? And our question is, will the glue hold? And our question is really a question about the shear stress that's being exerted on the glue. Okay? The strength of a material is described in terms of a maximum stress that it can withstand before it fails. So in this case, it's the maximum shear stress for the glue. Here we write sigma S, that's shear stress, and then the U underneath means ultimate. So the point at which it will fail. And the maximum strength of a typical epoxy might be 5 million pascals. Or more commonly, 5 megapascals. By the way, epoxy can also support tensile stress. If you glue two things together, it's hard to pull them apart. And the typical strength of an epoxy is much higher. It's 40 megapascals. Oh my goodness. You have to there we are. Well, you have to bear with me while I struggle with the notepad here. Okay. All right. So let's go back and let's see. So now in this problem, the shear stress is a force divided by an area. So first, what's the area? Well, what do you think it is? Okay, the area is the area of the glue joint, which is which is 10 by 10 centimeters. Or 100 square centimeters, which is 0.1 meters squared. No, I'm sorry. .01 meters squared. 10 centimeters is a tenth of a meter, so a tenth of a meter by a tenth of a meter gives a hundredth of a meter squared. What about the force? Well, the force is mg, and here m is equal to the density times the volume. And so that's the following. It's 8 grams per centimeter cubed times the volume. And the volume is the length times the width times the height. Or 500 cubic centimeters. Okay? Okay, to continue, now we have 4,000 grams times G. All right? And we want to get from this the force in newtons per meter squared. All right, so we're just about done. One little pitfall I want to point out to you, you've probably already seen it. Notice that our mass is measured in grams here, but we want to get a force in newtons. So note that 1 Newton is 1 kilogram meter per second squared. That is, it's an SI unit. Mass is measured in kilograms. And so we have to convert our 4,000 grams into kilograms in order to get the right answer. That's easy enough. We simply have to multiply by 10 to the minus 3 kilograms per gram. Then the gram unit will cancel out and we'll be left with a force in newtons. Okay? So finally, we have 4 kilograms times 9.8 meters per second squared, and that gives us it gives us 39.2 newtons. Great. Well, finally then, the shear stress is just this force divided by this area here. So we have 39.2 divided by 0.01, or 3,920 newtons per meter squared. Okay? If we like, we can write this as 3.92 kilopascals, and we're done. And we can see, of course, right away that this is much, much less than the shear strength of epoxy, about 5 million pascals. So we're in the clear. In fact, you can jump up and hang on to this block, and your weight plus the block's weight still won't break the epoxy. All right, let's stop here.